You can see my screen and hear me all right? Awesome. Thank you. So welcome to a new lecture. Today we'll be learning about data efficient image transformer. And first we will understand the intuition behind what was different about this model and what other models is a data efficient transformer most similar compared to. And in the second part of the lecture, we'll be building one from scratch. So we have already covered vision transformer. So the good thing about today's lecture is if you understand vision transformer and its coding properly, data efficient transformer, you will feel very much similar, because 95% of the things are very similar with respect to what vision transformer did. But data efficient transformer did something amazing, which made it significantly better in terms of training efficiency compared to vision transformer. One announcement that I have is we have migrated the website to a newer platform. And in this process, around maybe 5 to 10% of the students are not able to get access to their existing courses in their dashboard. So what you can do is you can just drop an email. I'm just putting it in the chat. Just drop an email here, just mentioning about the course name and that you are not able to have access. We'll fix it. All right. So now let's look at data efficient transformer. This paper was published in around 2021, and it was from Facebook AI Research. So the paper title is Training Data Efficient Image Transformers. So this DEIT is Data Efficient Image Transformer. So it is for images. It is making use of transformer architecture, and it has a few more things. So the other main idea that was introduced in the paper is distillation. You may have heard of the concept of teacher-student model. So we will look at it in detail today. What exactly is a teacher-student model in deep learning, and how that idea is also known by the term knowledge distillation, and how this knowledge distillation is utilized in data efficient transformer for making it significantly better compared to vision transformer. So if you think about vision transformer, the main problem with vision transformer, number one problem was that it required huge amount of data. The data set that was used for training the base vision transformer model was a 300 million image data set called JFT data set, which you will see in their paper. But this JFT data set mentioned in the paper, it's not a publicly available data set. It's Google's own data set. So this was a problem. Second problem was that the number of parameters in their state-of-the-art model in vision transformer, if I am not wrong, it was around 600 million. So it was not a very small model, 600 million parameters, around 300 million images in the training data. And it also required multiple days of training using multiple GPUs. So computationally, it was very expensive. But the vision transformer, which was trained using all of these, resulted in SOTA, state of the art, at that moment. And it actually overtook what convolutional neural networks managed to accomplish up until that point. So you know that 2012 to, let's say, roughly 2020 or around 2021, those were the years when CNNs completely dominated deep learning or computer vision. But then around 2020, when vision transformer was introduced, transformer architecture started becoming popular. So the reason why we are discussing about data efficient transformer is that it is the next logical succession, since we already know how vision transformers work. So CNNs had something good going on for them, mainly called as inductive biases. But now we have models with billions. So yeah. So in the context of images and in the context of the speed with which you can operate, this is not a language model. This is a image-based model. So 600 million model compared to, let's say, data efficient transformer with only 84 million parameters, it is large. Today, there are even bigger models, but the whole idea here is that how do you train a reasonably good model with low number of parameters, with less input data, basically small training data size, and still achieve something close to state of the art. So this was the problem that researchers were trying to solve. So in CNNs, they have something called as inductive bias. That most two famous inductive biases are locality, and second is translation invariance or translational equivariance. There is a very nice GIF which I want to show you. If you search, and if you go to Google Images, I'm not sure if it is popping up right away. Let's search inductive bias. I'm not sure if it is showing up. Let me check if I can find it on my own Miro board. It was a very, very nice GIF, which would have been nice to show you. Anyways, we'll check it. It was showing up until yesterday. But basically, translational invariance is the idea that it doesn't matter where spatially in the two-dimensional space where your feature is located in an image, your CNN will capture it. So if you have a big image and let's say you have a CNN which can recognize circular features, it doesn't matter where the circular feature is located, it will capture it because CNN operation, the convolution operation covers the entire XY dimension as it goes from top left to bottom right. So the bias, the reason why this is called inductive bias is that inherently the operation of convolution is making some assumptions. It is assuming that features are locally present and features irrespective of in which locality it is present, those features can be detected using certain type of filter. But we have discussed this in probably the beginning part of this course that this is not necessarily always a good thing. For example, look at this example. Here, if you are in a self-driving car, and let's say there is a person who is crossing the road, despite it being a green signal for the cars, the pixel where the person is present, maybe the person is here. So person is over here and red signal pixels are over here. So the actual physical distance between the pixels where the person is and the pixels where green signal is shown, they are actually far apart. But still, in this context of the image, those two sets of pixels are highly correlated. So there has to be some sort of global attention mechanism, a mechanism where irrespective of the pixel distance in the image, you should be able to make meaningful things out of that full context. And only then, let's say in this case, you will have a self-driving car which may work based on certain architecture. It should not run over the person just because you have a green signal. So this is one reason why people were so interested in bringing transformer architecture to images, because in transformer, it doesn't matter what is the length of the sentence that you're inputting as long as it is within your context window. One famous example that we discussed in the early part of this course is if you have a sentence that looks like the teacher who was teaching a difficult concept to the students, I'm not writing the whole thing, smiled. So here the smiled action is performed by the teacher, not by the students, but the words, these two tokens are far apart. They are one is at the right at the beginning, one is at the end, but still the attention scores between those two tokens should be high enough for teaching your model that actually teacher and smiled are very closely related to each other. So same concept applies to images. When you convert your images into patches and patches into tokens, it doesn't matter the physical separation between the patches. You can learn relationships between the far apart patches. So this was the reason why people were pushing towards transformer based architecture. But the problem was that in vision transformer, as I mentioned, you need huge data set and you need long training schedule. Simply means you need more number of GPU compute. So this was the main issue. And there is actually one sentence in the DEIT paper, which they have borrowed directly from the vision transformer paper. Look at this sentence. The paper concludes, transformers do not generalize well when trained on insufficient amounts of data. So this sentence in double quotes is taken directly from the vision transformer paper itself. So the paper itself says you can't have a good generalizable transformer model unless you have a huge training data set. So this was the problem that they were trying to solve. And this JFT 300 million is the data set on which vision transformer was trained. And it had 300 million images. And the size is also mentioned in, I think, one of the last tables of this paper. This is actually a very nicely written paper. I think if you try reading it, in fact, I am putting out a video on reading this paper sometime later. But if you read this paper yourself, I think 80% of the things you will understand in the first attempt itself. So how does patches solve inductive bias? Don't you need movement? Yes. So patches do not solve inductive bias. So inductive bias is not necessarily a bad thing. Inductive bias is a good thing, because that way, even if features are present in different portions of the image, it can be taken into consideration. Inductive bias is a bad thing because of its locality. It's not a bad thing because of its let's say translational invariance. So inductive bias is some inherent assumptions present in the convolution operation, like the fact that features are present locally. And that's the reason why you could simply use a 3x3 filter on a 224x224 image, because this 3x3 filter will capture local textures, local edges, etc. And those extracted features are enough to represent the data that is present in the image. So that is one bias. Another bias is it doesn't matter where those features are present in the image, whether it is top left, bottom right, doesn't matter. You will capture those features. So this was considered to be a good thing for a very, very long time. The only time when this was an issue was that convolutional neural networks could not capture long range dependency. It could not capture the fact that if you have a patch of pixel at the bottom right corner and another patch at the top left corner, and if they are having very high correlation, it's difficult to capture because the filters themselves are very local. It's constrained to simply 9 pixels. Yes, with multiple convolution blocks in series, you can increase the effective receptive field, but still CNNs struggle with the global context. And if you increase the effective receptive field by adding more layers, as you saw from the nano VLM lecture, the number of learnable parameters simply blow up in the later layers. So yes, CNN was the state of the art until certain point. And if you look at the comparison between CNN and data efficient image transformer, there is very high similarity, but the global context is still missing. Long range dependency is still missing. In one of the next lectures, when we discuss Swin transformer, which is shifted window transformer, you will understand how you can bring convolution operation along with the long range dependency capturing effect of transformer. So at that point, all the dots will be connected for you. But here, let's focus on just the transformer part, where we will try to figure out how to have smaller data set. Unlike 300 million images, can we just use a data set with 1 million image or 1.2 million image? So in DEIT, they said their value proposition is that they will only use one training data set, which is the ImageNet 1K. It's called ImageNet 1K because the number of classes is just 1000 classes. So it will be like a 1000 class classification problem. Total number of images is roughly 1.2 million, which you will split into train and validation. Now, the goal was, how can you meaningfully train a transformer like a vision transformer on such a relatively small data set and still get some results, some classification accuracy, which is comparable to state of the art. So this was the problem that Facebook was trying to solve at that time. So in DEIT, this paper, by the way, has around 10,000 citations, which is very respectable considering that it's only been around 4 years or slightly less than that. And so this is just the snapshot of the abstract part of the paper. I have just pasted it here so that you will recognize when you later want to read the paper. And this is the part which I mentioned, where they were directly quoting from. This was interesting because Vision Transformer paper, they concede that, yes, for small amount of data, it does not work. Vision Transformer model does not work. So what these guys did was they introduced the idea of teacher-student model in the context of teaching a transformer. So let me first show you a diagram, which before I go through this text, to make you understand the idea of what is a teacher-student model. So this is also associated with this term called knowledge distillation, or KD. And you might have heard of the term knowledge distillation in the context of large language models also. Most of the models have their distilled version available. So the idea is this: you have two neural networks. First one is a large neural network. Second one is a small neural network. Now, large neural network might be an already pre-trained one. So this is already trained. You are not going to train this anymore. But your goal is, how can you teach a small neural network with less amount of training data such that it can be almost as good as the large neural network. So in effect, you are trying to compress your teacher, or you're trying to compress the knowledge that your teacher has into a student model. So what is done is the following. You will have a training data set. Consider that the training data set is ImageNet 1K. So this is a significantly smaller training data set. Instead of 300 million data points, you just have 1 million data points. Now, what you do is you will pass the training data set. So let's say it's an image of a cat. It will be passed through the large neural network, which is the teacher model, and teacher will make its prediction. So let's say if it is a 3-class classification instead of 1000-class classification, you will get softmax scores from the teacher. So if the classification is, let's say, cat versus dog versus background, BG, your scores might look like 0.8, 0.1, 0.1, something like this. Now, these predictions made by the teacher, these are called soft labels. Why? Because if you were to make it into a hard label, you will say, teacher is saying with 80% certainty that it's a cat. And because of that, we will say it's a cat. But that will be hard label. Hard labeling would look like something like 100. So if we were to convert this using argmax into this format, like one hot format, it will be like a hard labeling. But this hard labeling, now you just tell me which among this has more information, B or A? Which one has more information present in it? Obviously, A has more information present in it. The reason is it tells you two things. One is, of course, it tells you that teacher thinks that this is a cat with high probability. But it also tells you that teacher thinks in this image, there is a 10% likelihood for finding a dog. There is a 10% likelihood that it's just a background. So these numbers actually give you slightly bit more information than the hard coded or hard labels. So what is done is let's say you denote the prediction made by the teacher by YT cap. Now, the small neural network, which will be randomly initialized. So teachers' weights and biases will be, of course, pre-trained weights and biases. So teacher, you will assume that it's already trained on a much bigger data set, right? Now your goal is, how can you have a student model which can learn a bunch of things from the teacher, not necessarily from the ground truth data. So now the small neural network will also make a prediction on the exact same image. Let's say it is the same cat versus dog versus background image. Now student will have its own predictions. We can call this as Y student cap. Now, usually what do? You construct a cross entropy loss. So usually we'll say loss due to, or loss cross entropy equal to minus sigma I Y student times log Y student cap for the ith class. This is the cross entropy loss, where Y student I is the ground. Actually, here I don't need the S. It's just the ground truth. So I just need to say YI. So YI is the ground truth for the current image for the current class. So here YI would look like 1, 0, 0. So if I equal to 0, Y will be 1. If I equal to 1, Y will be 0. If I equal to 2, y will be 0. And log of y cap will be whatever prediction student is making. And let's say the prediction made by student is 0.7, 0.15, 0.15. Then you can simply construct a simple cross entropy loss. And this is what you normally do in the absence of teacher. But now in the presence of teacher, what you do is you don't just consider the ground truth, which is the actual label of your image. You also consider the predictions made by the teacher. So these predictions are considered to construct the loss function. We will see in a moment what exactly does the loss function look like. But just keep this in your mind that to construct the loss, you are considering, in this case, three things. One is the actual ground truth. One is the soft labels or hard labels by the teacher. You can do both, but basically the predictions made by the teacher, that is considered, and predictions made by the student, that is also considered. Now, what is this loss used for? Do we use this loss function to modify the teacher? Yes or no? We don't, because we are not training the teacher here. Teacher is anyway a big model. If our goal was to train the teacher, it would take a long computational resources, long time for doing the training. This loss is only used for training the student. So we perform the backpropagation where the gradient of these losses with respect to weights and biases, basically parameters of the student, is calculated. And then based on that, we modify the parameters of the student network alone. Teacher will remain untouched. And if you do this, essentially what will happen is now student is learning two things. One is student is learning that, hey, I have to make predictions that are, not deviating too much from the ground truth. At the same time, student is also learning that I have to make predictions that are not deviating too much from what my teacher thinks is the ground truth. So yes, and we can do this just with soft label without the ground truth. So usually the way it is done is you will have a parameter. So total loss, let's say global loss, is something like alpha times cross entropy loss plus 1 minus alpha times. You will construct another loss. So let's say this is cross entropy loss between student and ground truth. And here you can construct another cross entropy loss between student and teacher's prediction. Let's call it as TP. So you will consider both of these losses, and then you will take a weighted sum of that using a parameter called alpha. If the value of alpha is 0, you are completely neglecting the ground truth. If the value of alpha is 0.5, you are considering the loss happening due to deviation from the ground truth and deviation from teacher's prediction equally. And if alpha is equal to 1, you don't consider the teacher's predictions at all. Okay, now there are a few questions. If proprietary images are present in our or teacher-student training, does not work right even if we have good teacher model. So if I understand the question correctly, if we are a company and we have a bunch of proprietary images and we have to train a student model, and for teacher, we pick some already trained model, and does it work very well or not, right? I assume that's the question you're asking, Manoj. It will still work to some extent as long as the baseline training data set on which teacher model is trained is similar to the kind of models that you have. If the kind of models you have is, let's say, synthetic data set, some non-naturally occurring images, right? Maybe it can be some, let's say, satellite images, which usually you don't have in training data set. But the pre-trained models that you have available on internet are mostly trained on ImageNet data, and ImageNet is mostly naturally occurring kind of images. So in such cases, just directly taking a pre-trained teacher may not be enough. You may have to do a little bit of fine-tuning of the teacher. Small amount of fine-tuning might be necessary. But otherwise, if the nature of images are very similar for your teacher and the student, then you will not need any fine tuning for teacher. You can use pre-trained image as such. Then what are soft label? Yeah, soft label is basically the direct logits, actually softmax coming out of the teacher. Softmax or logits both. But it won't be like a one hot encoding format. Like it won't be like 1000010, etc. Is alpha learnable? Typically, alpha is not learnable. It's more like a, I would say, hyperparameter. I mean, yes, you can call it as learnable, but it's not a parameter. If anything, you can call it as a hyperparameter. So yes, you may try to find better and better alpha values for figuring out how much weightage to put for teacher, error due to teacher, how much weight to put for error due to ground truth. But in many cases, I have seen alpha values just 0.5. In today's lecture also, we'll initially use 0.5, but I'll just show you how to change the value of alpha and get varying validation accuracy. Okay, if we have hard labels, what are the consequences? Excellent question. I'll show you one. So this is one example that is mentioned in the original paper. This is not a difference between hard label and soft label. It's a difference between using labels from the ground truth versus using labels from the teacher. Let's say I have an image like this. And this image is a 3-class classification. So if a cat is present in the image, it will be cat. If a dog is present in the image, it will be classified as a dog. If nothing is present, it will be background BG. Now let's say I have a cat here in just the top bottom left corner. Now you know that image augmentations are very usually routinely done for your training data set, so that by cropping, by randomly flipping, random rotation, etc., you can create more data points so that your training can be more efficient. More efficient meaning you get a bit more diversity. Now consider the fact that you are very likely in this case to crop like this. Okay, now your data point is this. What should be your prediction looking like? Should it look like 1, 0, 0? Or should it look like 0, 0, 1? The prediction. So the question is, this is your image. This red color thing is your image. In your image, there is a cat, but you did random cropping and your cropped window happened to be this. If that is the case, your prediction should look something like 0, 0, 1, correct? But let's say now what are you comparing your predictions against? You are comparing your predictions against ground truth, let's say, normally. Ground truth is what? Ground truth is this is a cat, because there is a cat in the image. So ground truth is 1, 0, 0. Okay. Now the problem is, if the teacher is absent in this case, let's say a teacher model is not there, your student is just compared against the ground truth for this augmented data set also, because just data augmentation is not going to change your labels. Labels will remain the same. So ground truth for this image as well as for this augmented image, both are the same. But now if you don't have a teacher for this input data point, your student will be forced to make a prediction saying it's a cat, although there is no cat inside this image, simply because the ground truth corresponding to this augmented data is 1, 0, 0. But now imagine the case where you have a teacher present. Teacher is anyway not part of training. Teacher is already pre-trained. So now if I was inputting this into a teacher, this augmented data into a teacher, and if the teacher is a very well pre-trained model, what kind of prediction will teacher more likely make? Will it make a prediction like 0.8, 0.1, 0.1? Or will it make a prediction like 0.1, 0.1, 0.8? First case or second case? Teacher will most likely make this prediction because you are just inputting an augmented data point, and teacher is not part of training. So teacher is not looking at label or anything. Teacher is simply making a prediction based on its already pre-trained weights. So teacher is more likely to make a prediction like this. And now consider two cases. In one case, you train your student just by looking at the ground truth. In another case, you train your student just by looking at the teacher's prediction. You are better off by somehow considering teacher's prediction also into account. I mean, this is an extreme case that I'm saying, but in this particular case, it's very clear that you should not just be considering the ground truth, right? So on an average, you have to consider the ground truth as well as you have to consider the teacher's predictions, where this, if you consider this cropping based augmentation as a special case. Now there are questions like, then what is the need for ground truth? Only teacher model should suffice then. Great question. The problem is teacher is not perfect. Teacher, you have no guarantee that for this data set, teacher has 99% accuracy. Teacher may have false positives, right? So teacher's accuracy may be 90%. You don't know. So as long as you have a good pre-trained model as the teacher, you assume that, okay, teacher has learned a bunch of things and it will take care of cases where augmentation will produce such problematic cases. And ground truth is your actual truth, because you also want your model to not deviate too much from your actual truth. So that's the reason why you will pick the loss function by considering deviation from the teacher and deviation from the ground truth equally or at the same time. All right. So that is the basic idea behind, is it possible to train SLM this way and bypass RLHF? Okay, great question. Actually, it is done. If you look at the DeepSeek R1 paper, if I remember correctly, they had a knowledge distillation also, which they did from a bigger model. So distillation is basically an idea where, okay, and before I come to that, just think about the good thing about this. Now, my teacher can be a CNN, right? Student can be a vision transformer. So although vision transformer does not have any advantages of the convolutions, translational invariance or anything like that, because vision transformer does not look at two-dimensional data. It simply considers patches, and only place where some positional or spatial information is coming is in the position embedding. Now, vision transformer, how can a vision transformer act like a CNN? Because we know that CNN is very good. What we can do is consider that this small neural network is a vision transformer, and consider that this teacher is like an already pre-trained CNN. We'll come to the loss function, how it looks like. But in principle, if this can be accomplished, then we can train vision transformer to make predictions similar to CNN. The way there is a great question. How does this differ from transfer learning? In transfer learning, the way it works is, the simplest way to think about transfer learning is, we have a model which is pre-trained. Okay. And let's say this is pre-trained on some public data set. Now I want to use the same model architecture. Let's say this is ResNet 50. And now I have some private data. Okay. And on this private data, I want to train a ResNet. Same model, ResNet 50. I want to train ResNet 50 here also. Now, in this case, transfer learning simply means you don't start from random weights. So instead of going with random initialization of the weights, you initialize the weights from the final stopping point of this pre-trained neural network. So in transfer learning, essentially what you're doing is, you are transferring the weights which are non-random. Why is it non-random? Because these weights were the result of a public data set based pre-training. And then you transfer those weights, and further you can train on top of it. So almost like fine tuning. And this is the idea of transfer learning. In this case, we are not touching the weights of this large neural network at all. We don't care about the weights of this teacher. We don't know about it. I mean, we may know, but we don't have to know. We simply have to know what prediction the teacher is making, right? We only know and we only care about the weights and biases of this small neural network. Now, teacher can be a big CNN model with large number of parameters, or it can be a 600 million parameter vision transformer itself. It doesn't matter as long as the teacher is well trained on a good data set. So it's completely different from transfer learning. In this, wouldn't we inherit all the biases the teacher model has, and how would we deal with any data drift? Yes. So this would inherit. Okay. We should not say that this will definitely inherit bias. We can only say that when we are training a model to make similar predictions as that of CNN, it is likely that some biases may be inherited. In fact, there is one paragraph in the paper over here. Just have a look at this paragraph. Our distill model is more correlated to convolutional neural network, CNN, than with a transformer learned from scratch. As to be expected, the classifier associated with distillation embedding. So forget about this. This I have not explained to you yet. But basically, there is a distillation embedding is closer to a connet, and there is another class embedding, which we have discussed in the vision transformer. I'm yet to come to this. But basically, here they are trying to answer the question, how do we know whether, does it inherit inductive bias that would facilitate the training, or does it not inherit inductive bias? And it's difficult to answer this actually, because the true definition of inductive bias is, are you inherently assuming a two-dimensional structure to your data set, are you inherently assuming that if some features are present at location A of the data set, and even if it's present in location B, whether those features will be captured or not? Such inherent assumptions are not there if you are simply using a transformer-based architecture. The only thing that is inherently present is, since you have a unmasked self-attention, you can construct global long-term dependency. That is the only thing that transformer guarantees. Nothing else. There is no other guarantee. But since we are trying to train a vision transformer using maybe a CNN teacher, yes, we can think of, okay, maybe the vision transformer may act like a CNN. So they have a table in the next page. I don't want you to get scared by looking at the table, but look at there are 6 rows and 6 columns, and it's perfectly symmetric. So basically they are comparing how much does the vision transformer deviate from a convolutional neural network, or how much does a data efficient image transformer deviate from a convolutional neural network. So if you are comparing predictions, I'll come to this table actually a bit later, because I want to talk about one important token. Otherwise, this table won't make too much sense. But just remind me once if I don't remember to come back to this table. And this is to answer the question of how do we know whether inductive biases from CNN is coming to this student model or not, right? We need to answer that. So let me first show you the architecture, and then I will go through the text. What is the data efficient image transformer architecture? The simple architecture is this. You have one additional token called distillation token. But if you only had these many, what would that be? All the patches plus class token. What is this? This is simply vision transformer. Here you have one more additional token called distillation token. And at the output, the context vectors corresponding to 2 tokens are considered. Context vector corresponding to the classification token or class token, and context vector corresponding to the distillation token. Now, this context vector will be, both of these context vectors will be used for constructing losses. So first is the cross entropy loss. So now let's talk about a little bit of mathematical detail of how to construct the loss. Once we discuss all of this, we can come back to more qualitative arguments. So let's say my class token prediction is something like the CLS token predicts something like PCLS is equal to, if it is cat versus dog versus background, let's say it is P1, P2, P3, where this is like a probability distribution. Now the cross entropy loss and the ground truth will be yi. So in this case, if it's a cat, the ground truth will look like 1, y equal to y1, y2, y3, where the value of this will be 1, 0, 0, the ground truth. So now what is the loss due to cross entropy, which we calculate for the classification token? It will be simply minus sigma I equal to 1 to 3 yi log p CLS token I. So it will be minus, this will finally boil down to minus 1 times log P1. Basically, this will be the loss due to cross entropy loss. This is the, and what is this? We are comparing how far the CLS tokens based prediction is compared to the actual ground truth. In the vision transformer, we were using CLS token for predicting what is the image, right? We were using it for classification. Let me open the vision transformer paper just to have the figure in front of me. So this is the vision transformer architecture that we had discussed. So first we do patching. So images are converted into patches of size 16 by 16. In this example, it is as if there are 9 patches total. Each patch will be converted into vectors. And if the vector embedding space is of 768 dimensions, each patch will be converted into a 768 dimensional vector. And along with these patches, one CLS token is prepended. So this is the 0th item is the CLS token. And for each token, what is this 0, 1, 2, 3, etc.? What are these numbers signifying? The 0, 1, 2, 3, it's the position embedding, because you need to add position information somehow. And in Vision Transformer, they had tried both learnable position embedding as well as a position embedding based on 2D spatial positioning. And they saw that both are equally effective. So they went ahead with learnable position embedding. And that's what we also did when we implemented Vision Transformer from scratch. And then once you have all these 10 tokens, these tokens are passed into transformer encoder blocks. And then from the final output, you will have a set of 10 context vectors, right? Every token will have one corresponding context vector. So here at the end, there will be 10 context vectors. But you don't care about all the 10 context vectors. You only care about one context vector, the context vector corresponding to the CLS token. Then that is passed through a multi-layer perceptron classification head, which will project that vector into a hidden space of larger dimension. And then from there, it will be projected into, let's say it's a 10 class classification, it will be projected into a 10-dimensional vector. So in the example of MNIST dataset that we used, the final layer was of 10 nodes. Now here, the architecture is exactly same. So I have made a different diagram to explain this architectures in a slightly better way over here. So this is, let's just follow the path of this token. So you have input image. Input image is converted into patches. So patching is done using dividing it into a fixed size. So each patch will be 16 by 16 or whatever the size is. So if image size is img underscore size, and if patch size is p, total number of patches will be img size divided by p, the whole square. You will have these many patches along the width and those many patches along the height. So totally in the image, you will have image size by p multiplied by image size by p, that many patches. Then you have prepending of the CLS token. So this is the initial embedding of the CLS token. This is the position embedding. And when you add these two, you get the final token embedding for the CLS token. Like that you have for all the tokens. And then at the end, actually this distillation token, you can add pretty much anywhere. I don't think there is anything that preventing you from adding the distillation token as the token number 1 or token number 2. But here, in the original paper, they added it as the last token. And then you will have several transformer blocks depending on how deep your transformer neural network is. In today's lecture, when we code, we can start with just a four blocks or something, and then we can play with it. And then you will have a classification head, which is only meant for CLS token. So here what comes is the context vector of the CLS token. Here what comes is the context vector of the distillation token. So this distillation token is for knowledge distillation. And then using the classification head, you will get what are the predictions made by your classification class token. So if it's a 10 class classification, you will have 10 logits. Similarly, for distillation token also, you will have 10 logits. Now, what is done is the predictions made by the, now you have to consider 4 things here to construct your final loss. One is predictions made by the CLS token, predictions made by the distillation token, predictions made by your teacher. Now, what is the teacher here? Teacher will be a CNN into which the same image will be input. And then that CNN will make a prediction. And you can take either the hard labels or soft labels. So if it is hard labels, it will look like one hot. If it is soft label, it will look like logits. So then you will consider these 4 things to construct your final loss. The predictions or logits from the CLS token, logits from distillation, then predictions made by your teacher, and the ground truth. So these 4 things now you have to consider to construct the final loss function. And this loss function is used only to train your vision transformer. This loss is not used to train your teacher. Teacher is untouched. You don't train the teacher, right? Okay, now let me look at some questions. Why we use 2 tokens, CLS and distillation? Take same CLS. Okay, excellent question. In fact, in the paper, they had done the exact same thing. Why do we need distillation token at all? Why not just use like basically two CLS tokens and just take the predictions from either one of the CLS tokens, something like that. So what they have done in the paper is, I think they might have answered a question from a reviewer looking at what they have done. So let me go back to that. Okay, so this is that section. Interestingly, we observed that the learned class and distillation tokens converge towards different vectors. So ideally, if CLS token and distillation token are learning the same thing, they should eventually converge towards the same vector. And how do we know the convergence? We will know the convergence by taking the dot product or cosine similarity. So the average cosine similarity between the distillation token and CLS token is 0.06. So here when they say 0.06, the average is considering different images. So you will input one image, you will see what happens to CLS token, and you will see what happens to distillation token, calculate the cosine similarity, do that for many different images, and the average cosine similarity is only 0.06. As the class and distillation embeddings are computed at each layer, they gradually become more similar through the network. So from going from the transformer layer number 1 till layer number 4 or 5 or 6 or whatever is the last layer, the cosine similarity between distillation tokens gradually increase. And in this model, for their base model, the last layer had high cosine similarity, 0.93, between distillation token and CLS token. But what they're saying is this is, but still it is lower than 1. And this kind of similarity, this kind of cosine similarity between CLS tokens context vector and distillation tokens context vector is expected since they aim at producing targets that are similar but not identical. And why do we say that? Because CLS token is aiming to produce targets similar to which one? Ground truth or teachers' labels? Ground truth. CLS token is aiming to produce something similar to ground truth. Distillation token is aiming to produce something similar to teacher. Then one thing that they did is they did an experiment. We verified that our distillation token adds something to the model compared to simply adding an additional class token. So this is what you had mentioned in the chat. Like, why do we need CLS and distillation? Why not take 2 CLS tokens? Then, so we verified our distillation token adds something to the model compared to simply adding an additional CLS token associated with the same target label. So what is the same? What does it mean by same target label? You have 2 CLS tokens. Both CLS tokens are now trying to learn ground truth. So instead of a pseudo teacher pseudo label, we experimented with a transformer with 2 class tokens. Even if we initialize them randomly and independently, during training, they converge towards the exact same vector with 0.999 cosine similarity. So it doesn't matter if we have 2 separate tokens. And if we are training both of them towards the same target, then it achieves nothing. Then because both context vectors will eventually converge to the same context vector. But here, the main key difference is that distillation token is not training on the ground truth. It is training on the teacher's labels, teacher's predictions. So that is the whole difference that is coming. Now you may have a question, which among these tokens, let's say I train my student model, which among these tokens will I use for classification? What do you think? Will I use CLS token or will I use distillation token for my predictions during validation? So in the paper, they have tried all the 3. They tried just with CLS token. We can also do that. They tried with CLS token alone. They tried with just distillation token. They also tried by taking a combination of both. And for their experiments, they found, I think if I remember correctly, they have a table. The combination of both worked better. Yeah, so this one was, so data efficient image transformer. This weird symbol, they are calling it as alembic notation, but this denotes that they have the distillation process in the model. So here they are considering both class and distillation token. And interestingly, so this was the most counterintuitive part for me from the paper. For them, hard distillation of the teacher worked better than soft distillation. Then I was reading, why is that the case? Why do we, because in my understanding, if you really want to know what the teacher is thinking, you need to take the soft labels like 0.8, 0.1, 0.1. Instead of taking 1, 0, 0, because 1, 0, 0 is not giving you information about the teacher's thought process. It's just giving you the final answer. So my intuitive thinking was that we need soft labels to get best output. So if somebody was to ask me what would I try, by default I would have said, okay, I will use CLS token plus distillation token for prediction, but I will use soft labels. I will not use hard labels. But here they found that hard labels work best. And what I understood is that hard label, the reason why hard label is working is, if we were using same type of models, let's say vision transformer for teacher and vision transformer for student, so a larger vision transformer for teacher and small vision transformer for student, if that was the case, soft labeling would have worked because both models are now looking at features in a similar way. But here in this paper, they used a model called, I think, EfficientNet or ResNet. So this was the model that they used, RegNet, with 16 gigaflops computing. So this 16 gigaflop is simply for processing one image, how many floating point operations do you need? So basically, if it is, say, 16 gigaflops, it simply means it's a bigger model compared to this one. But they are using CNN as their teacher. So because teacher is a CNN and student is a vision transformer, the way in which they are looking at the features are completely different, because CNN is looking at the features from the convolutions point of view. Transformer is looking at the features from an attention weights point of view. And because of that, and that's the, I mean, it's a very qualitative reasoning. I still don't know how to mathematically justify it, but qualitatively it says, because of this reason, hard distillation works better than soft distillation. Okay, does the hard label use cross entropy loss? Maybe the dichotomy of 1, 0 is increasing the error. Yes, it does use cross entropy loss. So we'll come to that. At that time, we can play with the numbers a little bit. Anyways, okay, but why distill token passed in student model? So distill token is not, nothing is passed into the student. I mean, distill token is not passed into the student model. Distill token is initialized in the student model. So when I read the paper for the first time, I got a little bit confused that I thought the distillation token was initialized using the output of CNN. I thought some feature vector was used to initialize distill token, but that is not the case. If that was the case, then it's like a bit cheating, because then CNN is somehow coming in your architecture. But distill token is initialized just like how your CLS token is initialized. Starting point is random. So because of that, you are not giving any unfair advantage to your network. The only part where teacher is coming into picture is in constructing the loss. Your distill tokens predictions are just compared against your teacher's prediction. That's the only place where indirectly CNN is influencing the vision transformer architecture. So this distill token is simply, please don't get confused, because you may think like this is cheating. Why? Because you may think like, oh, I have a CNN, I extract features using this CNN, and using those extracted features, I construct a distill token. And then I have a CLS token and distill token. And both of these are now passed into a vision transformer model. And then I have, again, CLS tokens context vector and distill tokens context vector. Let me just delete this. And then this is compared against the ground truth. And this is compared against the teacher's prediction. So this is what I initially thought what they are doing. But this thing is not there. Teacher is not influencing the distill token directly at all, right? So please understand that there is no, then I thought, oh, but isn't this obvious? If CNN is influencing distill token, then isn't it obvious that this will be a good model? Because you are directly taking the features from CNN. But here you are not taking features from CNN. You are taking only the predictions from the CNN. All right. Okay, now let us look at the loss function, which is probably the most important thing here. So I have written some terms here, so I will go through it one by one. So now let's look at the loss, cross entropy loss. So LCE. This will be minus, this is the easiest one, I equal to 1 to C if you have C classes, yi, where yi is the ground truth, log pi, where pi is the prediction made by the CLS token. So now this is the cross entropy loss due to disagreement between predictions made by CLS token and the actual ground truth. Now we need one more loss due to, let's say, student teacher, and this is called as KL divergence. And it's very interesting the way it is calculated. So the formula is over here. I will give you the intuition behind the formula. So the loss due to disagreement between teacher and distillation token is given by this formula, T square. Please don't get worried by looking at this. I will explain every single term. but the formula is t square multiplied by sigma I equal to 1 to c. So sigma I equal to 1 to c is you are summing over different classes. So if it's a 10 class classification, the sigma will go from 1 to 10. Then this is prediction for the ith class, probability prediction for the ith class made by the teacher. Then log of pti is probability prediction made by the teacher for the ith class. And here again in the denominator, you have probability for the student for the ith class. Now I'll explain what this PT is. PT is simply the probability which you calculate from softmax. So let's say I have a teacher, I have distill, then I have CLS, and I have ground truth. And say I have 3 classes, cat, dog, and background. And let's say it is a cat. So ground truth is 1, 0, 0. Now, let's say my teacher, which is a CNN, is making a prediction like 0 0.8, 0 0.1, 0 0.1. And let's say my CLS token is making a prediction that looks like 0 0.9 or maybe 0 0.8, 0 0.1, 0 0.1. And distillation token is making a prediction like 0 0.9, 0, and 0 0.1. Now, LCE, which is the cross entropy loss, and this is for the loss between CLS and ground truth. For that, you compare these two. So finally, what will be the loss? If you can just give me one number, minus log, what should it be inside? Minus log 0 0.8, because it is minus sigma log minus yi sigma, sorry, minus sigma yi log pi. So yi is 0 for this, yi is 0 for this. So only one term will survive. So it will be minus 1 times log of 0 0.8, which is equal to minus log 0 0.8. Why do we have negative sign? Because probabilities are between 0 and 1. So logarithm of a number less than 1 will be negative. And to convert it into a positive loss value, that's why you have a negative sign here. So this will be simply the cross entropy loss. But this part is easy. Now let's come to the difficult part. Difficult part is how do you construct the loss between these two? Now tell me one very, I would say, bold thing your student is doing. So this is student. This distillation token is now the student, and this is teacher. Do you think this is a good thing? This 0. Student is saying that this item is 0. Is this a good thing or is this a bad thing? Why is it not a good thing? If it's a good thing, why is it a good thing? Not from a mathematical perspective. I want it more from a, I would say, qualitative or logical perspective. The reason why this is not a good thing is teacher is first of all not at all sure whether, here student is saying with 100% certainty that it is not a dog, right? That is what student is saying. I am 100% sure this is not a dog. But teacher does not have that kind of certainty. Teacher still has some doubt. Teacher still thinks this image is 10% a dog. So while teacher is making a, I would say, such a less confident probability score for this, student is saying something with high certainty. That cannot happen because student, we are trying to teach the student what the teacher already knows. So if student makes such a high confident prediction, it should be penalized heavily. And how heavily? How much should be the penalty in this case? It should be as close to infinity as possible. Because see, student is making a completely wrong, completely confident prediction here, while teacher does not have that kind of a confidence. And how does the penalty become minus infinity? Let's look at the formula. According to the formula, loss due to KL divergence, and KL divergence is used for constructing how much does one probability distribution vary from another. You can say it will look something like probability due to teacher multiplied by log pi. So probability due to teacher, which is 0.8 multiplied by log 0.8 by 0.9 This is the first item. So this 0.8 is this teachers, this 0.9 is students. So this ratio is students prediction by teachers prediction. And this vice versa, teacher's prediction by student prediction. And this 0.8 is P due to teacher. That is the first term plus 0.1 times log 0.1 by 0 plus 0.1 times log 0.1 by 0.1. Now this term, what would this term be? 0, because logarithm of 1 is 0. This would be very high number, inf kind of number. And this will be some finite number, okay? So see, we are penalizing the distill token heavily in this case because it is making such an overconfident prediction. What if student's prediction was something like this? What if student made this kind of a prediction? What should be the penalty for the distillation token in this case? And it will be 0. How? 0.8 multiplied by log 0.8 by 0.8. That's the first term plus 0.1 times log 0.1 by 0.1 plus 0.1 times log 0.1 by 0.1. So all these terms will be 0 because for every single item, teacher and student are assigning the exact same probability scores, which means whatever is there inside the logarithm, those ratios will be 1. So the loss will be 0. Now let's look at another case. What if my teacher was very confident? What if I had something like this? Now what would happen? Now my loss will be 0.8 multiplied by log 0.8 by 0.8, first term. Second term will be 0 multiplied by log 0 divided by 0.1 plus 0.2 multiplied by log 0.2 by 0.1. Now I'm just picking an extreme case, but tell me this. I have x and log x, okay? And in this case, let's say I have a formula that looks something like this. X log x, where x tends to 0. What is the output of this? Let's say y equal to this. Is this, what is the value of this? Can anyone ask ChatGPT or something and let me know? So x tends to 0, log of x. Why do you think it's not defined? Just think about it. Which one will decline faster? So log of a small number, you know, it's log of 0 is negative infinity. So log of x will be something tending to negative infinity if x tends to 0, right? But then to counter that, you have an x tends to 0 multiplication outside. My intuition says that this logarithm falls a bit slower compared to how x, this is linear and this is logarithmic. So my intuition says that this will be close to 0. This will not be close to negative, like undefined. But let me ask, what is x log of x if x tends to 0? Right, it should be a negative number, but it should be close to 0. So as x tends to 0, x log x tends to 0. The reason is the logarithm of x is not approaching negative infinity as fast as x is approaching 0. Because x is linear and logarithm of x is, it's logarithmic. So I think here, and here there is this rule, right? L'Hopital's rule. So you can write this as log x divided by 1 by x. And it's written as L'Hospital's rule, but it's pronounced as L'Hopital's rule. And then you can say that if this is x tends to 0, then you can take the derivative of both. So if you take the derivative of both, what is derivative of log x? If it is natural logarithm, it's 1 by x, right? If I'm not wrong. And the derivative of the denominator is minus 1 by x square. So then this will be minus x square by x, which is equal to minus x. And what is minus x if x tends to 0? It will be a negative number and it will tend to 0. So even in this extreme case, this formula is still okay. I mean, what I'm saying is there is no mathematical instability in this formula. Even when teacher is making a confident prediction, it is okay. But when student is making a confident prediction, there is no mathematical issue. It's just that the error will blow up. So now you can add those two errors, those two losses to create your final loss. One thing I forgot to mention here is you will have logits first before you get the probability, right? So how do you get the probability? You will first have logits like Z1, Z2, and Z3. And from this, you take softmax to get P1, P2, P3. Now, usually, how do you do softmax? E raised to, so Pi equal to E raised to Zi divided by sigma E raised to Zi, where I runs from 1 to 3. Now, one thing that is done is, let's say I divide this by a t, and if t is greater than 0, will my softmax become 1 more sharp or less sharp? If t is greater than, sorry, I don't mean to say t greater than 0. I meant to say t greater than 1. If t is greater than 1, will it be more sharp or less sharp? Softmax will become less sharp because now you are taking exponents of smaller numbers. But if t is less than 1, if t is a positive number that is less than 1, then this effectively this number is increasing. So whatever is inside the exponent will become a big number if t is less than 1. Then softmax will become more and more sharp. So a temperature parameter is introduced here in this calculation. Just look at this formula. In the construction of softmax probabilities, you are taking exponent of Zi divided by sigma exponent of Zi, but you introduce a temperature parameter so that the softmax is the softmax distribution is made less peaky. But there is one issue with this. One issue with this is that when you take the derivative of softmax, because for back propagation, you need dou L by dou weights, where softmax will be somewhere there inside the loss function, right? The problem is a 1 by t square will pop out. A 1 by t square term will pop out, which means if your temperature value is so high, if it's higher than 1, then it has a tendency to kind of reduce the magnitude of your gradients. So what is done is finally, if you look at the final formula, they have a t square term outside to cancel this t square effect when you are taking, when you are finally taking the derivative. So the final formula is something like this. Loss due to teacher is P probability distribution due to teacher multiplied by log of ratio of the teacher's probability divided by student's probability prediction. This we already saw. But this probability itself is calculated from logits using softmax. But inside the softmax, there is a temperature smoothening or temperature softening. And to minimize the effect of gradients getting lower in magnitude while taking derivative, because while taking derivative, you can mathematically show that an extra 1 by t square term comes. To cancel that 1 by t square term, you introduce an extra t square term. Now your total loss is simply LCE plus L teacher. What is CE? Cross entropy loss. How is it calculated? Between CLS token and ground truth. And how is teacher's loss calculated? It is calculated between distill token and between teacher's predictions. So how do you Y teacher cap? So, and then you can combine those two. And while combining, you can also do something like this. So L equal to alpha or lambda times LCE plus 1 minus alpha or 1 minus lambda times L teacher. We can define this to be 0.5 so that equal weightage is given to both. But if it is not, then teacher and student will have different, I mean, teacher and CLS token will have different weightages. So this is the final loss function. So this is essentially how data efficient image transformer works. It's very simple, completely same as vision transformer. The only points you have to discuss it, notice is distillation token is randomly initialized. It is not initialized using CNN. It is as randomly initialized as the CLS token. So there is no, I would say, discrimination between these two. For teacher, in our experiments, we will use pre-trained CNN. And in the paper also, they tried pre-trained CNN as well as pre-trained vision transformer, a bigger vision transformer model. They saw that pre-trained CNN, using pre-trained CNN was better. Next is the CNN, which is the teacher, can be used for producing soft or hard targets. In the paper, they tried both soft targets as well as hard targets. And these targets are how you compare your distillation token against. And they saw in the paper that hard target was better. Maybe one thing I'm curious to know is if instead of CNN, if they used a vision transformer, will the soft target be better to use? That question, I don't think the paper has answered. Then one more thing to note, CNN does not directly influence the value of distill token. CNN only indirectly influences. How does it happen? The CNN's predictions are tried to be matched with distillation prediction. If the predictions is mismatching, that will cause a huge loss. The loss will result in changing the parameters inside your vision transformer. And based on that change, now the next prediction of distill token will be different. So that is how distill token is influenced by the CNN, not directly, it's indirectly. Just keep these points in your mind. This graph is the figure 1 of the paper, which showed their result. So what they have is this red color dots are all data efficient image transformer with distillation. And you can say that with distillation, the accuracy, so y-axis is accuracy, top 1 accuracy for ImageNet dataset, validation set, and here it's the speed with which it can process images. Basically, how many images per second you can infer on. So here you can see that. So in general, if you are on the right-hand top corner, you are good. If you are on the left-hand bottom corner, you are bad. It's not a good model. And here, unfortunately, vision transformer, the vanilla vision transformer, which we learned 2 lectures ago, they happen to be on this bottom left corner. They are relatively slow for the same comparable architecture size. And their accuracy is also slow, but they had a vision transformer model which was very big with 600 million parameter. That was, of course, the state of the art with 88% accuracy. It's beyond this. But here, if you compare it with EfficientNet, so among the CNNs available, EfficientNet was one of the best state of the art models. Your data efficient vision transformer performs better than EfficientNet. And I think this is also data efficient vision transformer without the distillation token. So distillation token is clearly taking you from here to here. So this is just like a vision transformer with a teacher. But this is vision transformer with a teacher and distillation token. So distillation token is indeed playing a huge influence. Just to answer how the distillation token is influenced, it's not directly influenced. See, distillation token's prediction, let's say the prediction is diverging from CNN prediction. Loss is high. If loss is high, gradient is high. If gradient is high, during gradient descent, weights will be modified. If weights and biases are modified in the architecture, for the same input, distillation token will now produce a new output. So that is how it is influenced. So CNN does not directly ask distillation token to change its values. CNN says, okay, here are my thoughts about the current image. What are your thoughts? Then distillation token will give its probability distribution. Comparing these two, loss due to KL divergence will be constructed. And if loss due to KL divergence is high, dou LKL divided by dou weights, where weights are the parameters of your vision transformer, this will be high, which means the way in which weights will get modified, Wi plus 1 equal to Wi minus eta, which is the learning rate, multiplied by dou LKL, or this is the total loss, but I'm just mentioning dou LKL here, divided by dou Wi. This will be a big number. So weights will get modified significantly if the gradient is high. When will the gradient be high? When the loss is high. When will the loss be high? When there is huge disagreement between distillation token and CNN's prediction. So that is how indirectly CNN influences the distillation token. It's not direct. It would have been direct if you were somehow pumping the values from CNN features here itself. But if you do that, that will be cheating because you are directly using the features from the CNN. Here you are not using features from the CNN. You are using only the predictions from the CNN. Okay, according to loss function, we are penalizing heavily distill token, confident prediction. What is the intuition? So that's what I said. So distill token is a student. And ideally, student should never make confident prediction unless teacher is confident. So unless teacher thinks that the labels are something like 0.80 and 0.2, here teacher is very, very confident that 100% it is not a dog. So if this is cat, this is dog, and this is background, teacher is 100% confident it's not a dog. If teacher has that kind of a confidence, then student is allowed to this is the basic principle of knowledge distillation. Then student is allowed to make a confident prediction. Otherwise, confident predictions can very well become wrong. So being confidently wrong is the worst thing a neural network can do. And how do you prevent the neural network from making confidently correct prediction? You prevent neural network from also making confidently. How do you prevent neural network from making confidently wrong prediction? You also, as much as possible, try to prevent it from making confidently right predictions. So high confidence for student, you penalize basically. All right. Now I think we know all the things that is there in the data efficient transformer. We'll get to coding, but let me look at a couple more questions. How does it work on custom data set, which is completely different from public data set on which teacher model was trained? Or do you think teacher's predictions will be incorrect here, mostly due to data drift? Yes, exactly. So if you think teacher is trained on a completely different data set, it will tremendously benefit to slightly fine tune the teacher on your custom data set. Now, what is the advantage of this? Fine tuning is not expensive. Fine tuning is an order of magnitude less expensive compared to pre-training, because you may be running for few epochs. You are starting with not random weights. You are starting with already existing good pre-trained weights, right? So in that case, you can start with a teacher which is slightly fine-tuned on the new data set. And then you try using that teacher for teaching the student. Otherwise, if you use just a vanilla teacher which is randomly trained on some random internet data set, it will not give you any good results, right? Good question. It's a good question. So now I think what we can do is please open your Google Colab. We can start coding. You will of course notice that there is a lot of similarity between how we coded vision transformer how we coded data efficient transformer. But it'll be fun nevertheless, because the more you code these things, the more comfortable you will get. So DeiT coding from scratch. Okay, so I will share the notebook link, but I guess it will get, so you will have to type along with me. Otherwise, it will take time to get updated. All right, so first is import module. So one nice way to put title is you can just put like this. So it will come as, hash also is needed. So imports, now let's import all the required libraries. Import torch for PyTorch, torch.nn, because you want to have nn.module passed into your classes, torch.nn as nn, then torch.nn.functional as f. So this is for getting various functions like cross entropy loss, and also for, if needed, for converting vectors into unit vector. You had seen that during the nano VLM lecture. And torch vision for PyTorch for computer vision. Then from torch.utilities.data import data loader. We will also need something called subset. The reason is I'll show you. Initially, I wanted to actually, let's remove this for now. We can train on the whole data set. So just data loader. Then from torch vision, import transforms, data sets, models. So transforms or data transformation, this is for loading batches, and models for constructing your neural network model. Import numpy as np, then import matplotlib.pyplot, splt. I think those are the only items we need. Then we can define device equal to CUDA if torch.CUDA dot is underscore available is true, otherwise CPU. So then just run that. Next is we can define some variables that we are going to use. So what are the variables? Batch size we will need. Let's keep it at 12. Image size probably, if we are using MNIST, it was 28 by 28. Patch size, last time in Vision Transformer, we used 7 by 7 patch. Then attention heads in that Vision Transformer, attention underscore heads, let's say 4 attention heads. Then embedding dimension, let's say it is 32 or something. And let's say number of classes in our final classification is 10. It's a 10 class classification. We'll be using MNIST. We can use other data sets also, of course. Then epochs for training. So here we are not fine-tuning the teacher. We are only fine-tuning the training the student. If we are fine-tuning the teacher, we may have one set of small number of epochs for teacher also, but here epochs for student, let's say 5. Then learning rate for student is something like 3 times 10 to the power of -4 or something. This we can play with. Then I'm going to define something called number of channels. Actual number of channels for our data set is 1. It's a grayscale image, but I'm going to define it as 3 because the neural CNN that we are going to use, it will expect 3 channel input. So let's keep it at 3. I'll show you how to expand the number of channels from 1 to 3. Then attention heads is fine. This is in the multi-head attention. Transformer layers. We will require, let's say 4 transformer layers are there. And then the temperature parameter that we are going to use in the KL divergence equal to, let's say, it should be greater than 1, let's say 2. Then lambda or alpha, which is the scaling factor for alpha or 1 minus alpha. Let's keep this at 0.5. So equal weightage is given to KL divergence loss and cross entropy loss. I think that's pretty much it, most of the variables. Next is importing the data. Now we have to define some transformations for this. We had done last in the Vision Transformer coding also, but let's first import the data. So train data set equal to, it is imported from data sets dot MNIST, and we want it in the root folder, and which is named subfolder named as data. Then train equal to true, and same thing for validation. So or testing, we can say test ds or val ds should be a better way to call this. Datasets.mnist train equal to false. Then we have to download this. So keep it as download equal to true, and copy paste that for validation. And then we have to define some transformation to convert it into tensor format. So transformations or transform actually equal to data underscore transformations. We are yet to define this, but we will define it soon. Transformations. So you transform both of these data sets. And then here we define data underscore transformations equal to transforms dot to tensor But before that, we have to have transforms dot compose. And so converting to tensor is one transformation. Another transformation is you have one channel input, you want to expand it to 3 channels because that is the input that CNN is expecting in this case. So transforms dot lambda, then lambda t, then t dot repeat. I mean, this is just basic syntax. No need to, spend too much time on the exact syntax, but basically it's just expanding into 3 channels, the input. And just close the bracket. So you have 2 transformations. First is transformation to tensor. Second is expanding the number of channels. I think I have an extra bracket. Yeah, I think we are good to go. And then we have to create our batches. So create train and val batches. Then we say train data loader equal to something, val data loader equal to something. And what is train data loader? Data loader of train ds. So we are loading it from train ds. And here we have to pass the batch size equal to batch underscore size. And shuffle equal to true. For validation also, it is exactly the same, except shuffling we don't do, and we are passing val ds. Shuffling is not needed. So now let's run these two, hoping that it works. So batch size is 12. Okay, there is some batch size not defined. Okay. All right, so now training and validation data set is ready. Now we can define our teacher model. So title teacher model. So teacher has to be a pre-trained model. So teacher equal to models dot ResNet 50. So we can simply use a ResNet convolutional neural network. Then what weights are we going to use? We are going to use some weights where pre-training is done on some ImageNet 1K or some data sets like that, public data set. So weights equal to models dot ResNet 50 underscore weights dot ImageNet 1K version 2. So one particular set of weights. So ImageNet 1K version 2 is a specific data set. We are just using those weights. Then what do we have to change here? Can anyone tell me in the chat? Okay, we imported the teacher model, but then we have to make a change to the teacher model, right? What is that? We can't use this as such. There is a small issue. Exactly. You have to remove the last layer because last layer here will have how many nodes in this case? 1000 nodes because it's a 1K class classification, but we don't need 1K nodes. We only need number of nodes equal to classes, 10 nodes. So teacher dot fully connected equal to nn dot linear teacher dot fully connected dot input feature. So in the last fully connected layer, we just need the input feature, how many ever nodes it has, but output feature should be same as classes. So output feature will be 10. And so if we keep it as 1000, it will be exactly same as what it was before, but here it will be classes. Then we say, since we want teacher also to be processed using whatever GPU or CPU, whatever we are using, we say teacher dot to device, whatever device is being used in our training. Teacher is anyway not being trained. We removed the last layer of the classification head. We did not remove the entire classification head. We removed the 1000 nodes. We removed the output features from the last layer. Input features, we kept it as such. So input features might be whatever, let's say 2048, whatever that number is. So it was a fully connected connections going from 2048 nodes into 1K nodes. Here we remove those 1K nodes. So 2048 is the input number of features going into that, into the final classification head. 1000 was the output nodes. But here we don't consider the output nodes. Output we keep as number of classes, which is 10. So we are not removing the classification head. We are removing only the last 1000 layers. But you need to use those same classes, otherwise need fine tuning. Not necessarily, not because you can think of CNN as a sort of like a feature extractor. So yeah, I mean, I agree that the last layer will be completely randomly initialized and its output may not be as good. So you may want to do a freezing of your neural network where all layers are frozen except the last layer. So these nodes should have some good weights. In this particular case, we are avoiding this entire pre-training altogether simply because the data set is a simple data set. So even the existing teacher model is able to extract data set in a good way. It's the most simplest data set. But if you were to use, let's say, CIFAR 100 or some slightly more complex data set, you will have to do one round of fine tuning. And I don't want to call it as fine tuning. You would have to do just one round of final classification layer training where everything is kept frozen except the last classification head 10 nodes, right? It's a good practice. Otherwise, you will not get a good teacher. Your teacher's predictions will not be good. But here, the good thing is we are not just relying on the teacher, right? We are also relying on the ground truth. Teacher, we are just relying to see what kind of feature extraction this teacher is capable of on our data, and finally, what kind of softmax probabilities are coming out of it. That's it. But it's a very, very good point. Okay, so now let's run the teacher model. Then now we can define the student vision transformer. So student VIT, and this fairly something that we had done before. We need a patch embedding, and earlier we had defined the MLP head separately and the transformer embedding separately, but this time let's not do that. We'll just say VIT class. So we have one class for patch embedding, one where we simply have the VIT vision transformer class. So class patch embed, and into this we have to pass nn.module. So it inherits the properties from this class. Then define underscore init constructor underscore, and then here we pass self and bunch of other things also we have to pass, but we'll come to that. Then super, so that you are now calling the init constructor of your parent class also. So this init constructor belongs to parent class. This init constructor belongs to the current class. And then we have to do a few things. First is we should create patches from input images. So I hope you remember some things from the vision transformer lecture where we created a con2D. So 2D convolution for patch extraction. So nn.con2D, where this 2D convolution had input features equal to number of channels, which was, in this case, it is 3. In the vision transformer, it was 1 because there was no CNN. There we were just using a vision transformer, and we did not mind whether number of channels is 1 or 3. But here the input that goes into our ResNet is 3-channel input. Just because of that, we expanded the number of channels from 1 to 3. So instead of just writing it 1 here, writing 3 is better, but I'm going to pass it as a variable. So classes we are passing. And here we say classes equal to classes. Then we need to know what should be the embedding dimension, because the each embedding dimension looks like a one output layer of the 2D convolution. So then we say embed underscore dim, and that we have to pass that also. Embed underscore dim equal to embed dim, which is 32, I think, as we defined above. And then this will result in width equal to number of patch. Now we have to define stride and kernel size. So kernel size will be equal to patch size. So we just need to say patch underscore size. So this we pass. Patch underscore size equal to, I forgot the variable name. Yeah, patch size only. Because we have to create non-overlapping patches. So kernel size should be same as patch size. Stride should be also same as patch size. So this we had discussed in detail in Vision Transformer lecture. If you want a brush up, just revisit Vision Transformer once. This part we had at least spent maybe 20 minutes on this section. Then we need to know how we don't add channel argument. So channel we are adding. Channel is basically number of classes only. It's just that the value of this is 3. So number excuse me, number of input channels in your input is 3. Number of output channels is equal to embedding dimension. Kernel is equal to my bad. I did not mean to pass classes here. I mean to pass channels. Thanks for, this is not classes. This is channels. Okay, thanks for catching. Otherwise, this would have caused a lot of issues in the downstream. But yes, this is channels, not classes. Because it's starting with C in my mind, suddenly I was thinking it has class channels. So this is channels, which is 3. Embedding dimension 32. Patch size is kernel size. This is stride. Then number of patches. So self.n is equal to, this will be image underscore size divided by patch underscore size. Where is that? Patch underscore size. And for this to be an integer, we use this floor operation and raise to 2. And image size is not defined. So image size we pass, image underscore size equal to image underscore size. And what else? Patch size is already there. Okay. So, and then we can define the function where this is executed for every single input. So forward pass self comma x. Then we say x equal to self dot projection of x. So this will create patches, but I hope you remember what we had done last time. We had to flatten these patches. So x equal to x dot flatten of 2, so that all the patches will now look like one. If there are 16 patches, it will look like along one dimension. And after flatten, if you remember, we had one more operation called transpose of 1, 2. The reason was we have a batch size. Our batch size is 12. We had a certain number of patches. Number of patches were image size is equal to n, but image size divided by patch size raised to 2. Then we should have embedding dimension. But by default here, embedding dimension will come first, and then only number of patches will come. But we want those 2 dimensions to be flipped. So there are totally 3 dimensions. First is the number of items in each batch dimension. Second item up until this point will be the embedding dimension. Third item will be the number of patches, but we want number of patches to be in the second dimension. That is why we are flipping or transposing along dimension number 1 and dimension number 2. Dimension number 0 is batch dimension. So far, we have used only one filter here. No, the number of filters, I mean, manually we have defined only one filter, but the number of filters will be embedding dimension. So number of filters is equal to 32 here. Please remember, number of channels in the filter equal to same as number of channels in your input. Number of filters is equal to number of channels in your output. So here at the output, number of channels is 32. So this operation will define 32 filters automatically. We don't have to do it manually. Batch first equal to false. So batch first equal to true we have to define, but that comes in the multi-head attention part. Here, I don't think we have to do that yet. And then just return x. So now the batching is done. No, not batching, patching is done. Then we define the class for vision transformer, which we can write separately. So here, patch embed. Then next will be student vision transformer class. So class VIT, where we pass nn.module, then define underscore init constructor where self is there and bunch of other things we may have to pass. We'll come to that. Then super init. And okay, now we have to define a few different things. First is let's define the patch embedding by creating an object for patch embedding class here itself. So self.patch embed equal to this class. So equal to patch embed. And then we need what? CLS token, we need embed token, we need token embeddings, we need position embeddings, all these things we need. So yeah, not embed token, distill token, dist token. Thanks for that. Yeah. Okay, so now let's define self.cls. Self.cls token was initialized as learnable parameter. So nn.parameter. So it will be initialized randomly, but it will be learnable. Then torch.zeros. Here it's actually not initialized as randomly. Otherwise, it would have been torch.nn.random, rand.nn. It will be sampling as a random numbers from the normal distribution. But here we can initialize as zeros, 1, 1, dim. So this one belongs to embed dim. This one belongs to batch dimension. This one belongs to the fact that you have n number of patches. And this embed dimension is the fact that each patch is of the dimension embed dimension. So embed dimension we'll pass here. Embed underscore dim. Okay, so that is self.cls. Then self.distill or distillation equal to also nn.parameter. It's pretty much exactly the same. There is no difference in the structure, but they will learn different things. So distillation is done. Then let's come to position embedding first. Self.position embedding equal to nn.parameters meter of torch.zeros. Again, we can initialize is at zeros, but then it will be learnable of 1 comma. What should the next dimension be? Last should be obviously embed dim. What should be this middle dimension? What should this number be? Just a number. What should that be? Or if not number, just give me like a variable that represents this. It should be number of patches plus 2, because n number of patches result from creating patches from images. But then you have CLS token in addition. For that, you have to add a position embedding. Then you have distill token at the end. For that also, you need position embedding. So whatever is the number of patches, you have to do plus 2. So let's say n plus 2, where n is the number of batches which we are yet to define. So n equal to, or self dot n equal to, we can say patch embed or patch embed dot n, right? Where is it? Yeah, n. So this will find the property of dot n from patch embed. I'm not sure if there is any. Okay, self.patchembed.n. Yeah, okay, now it's fine. And this maybe we have to define this as self.n, but let's see, self.n plus 2. Or this can be just since it's independent of, I think this is also fine. So n equal to self.patchembed.n. Self.patchembed is the object that we are currently looking at. And patchembed.n is this n from here. Patchembed is the object corresponding to this class. Okay, position embedding is this. And then we have to define self.transformer blocks equal to nn.sequential. And here we have to actually add bunch of things, right? So one interesting thing is, actually, let's not write it here. It will come later. We just need to define what is this. So nn dot transformer encoder layer. So here we are calling this transformer encoder layer. In Vision Transformer, we did not call transformer encoder. We just called multi-head attention. Then we constructed the transformer encoder by adding residual, adding multi-layer perceptron, etc. separately. But here by calling transformer encoder, all of that is internally taken care of. We just need to pass the embedding dimension, number of attention heads, number of blocks, just those three things, and batch first equal to true. So embed dim, we have to pass. Then attention heads, attention underscore heads, we have to pass. Then number of, or rather dimensionality of dim equal to 4, which let's say is the dimensionality. I don't know if it is divisible by. Okay, let's keep it. We'll come back to this, whatever the dimensionality of my query key value space should be. This one I'm doubtful. Let's keep it. Attention heads we have not defined. So attention underscore heads equal to attention underscore heads. Then dimension equal to 4, and then batch first equal to true. I think that's mostly it. But then you need how many such transformer blocks? So this dimensionality is now the dimensionality of the key query value space. I think it is better if I just say this is equal to dim equal to something divided by attention head. So embed dim underscore dim divided by attention heads. And then this I can just pass here. QKV dim equal to this. Okay, so I think this is better. And I just need to now ensure embedding dim and attention heads are divisible. So embedding dim is 32. Where is that? 32. And number of attention heads are 4. Okay, 32 by 4 is fine. But if we use 32 and 3, this will cause an error because number of heads and embedding dimension, they should be divisible. But one more thing is, what if, but I need bunch of transformer blocks, right? This is just one transformer encoder. So how do I write this? We need to sequentially add. So we can, one thing is we can say nn.sequential of, then I can write this 4 times. I can copy paste whatever is this 4 times, but oh yeah, batch first equal to true. That automatically came. Temperature, it's not temperature, it's true. So I can copy paste this 4 number of times to say that, okay, now I have 4 transformer blocks in my Vision transformer, but what if then I have 20? I can't copy paste this 20 times. So then I can do something like this. Inside this, I cut and paste this. And for dash in what was it? Attention or no, transformer blocks, I think variable name, transformer layers. So I can pass layers here, layers equal to this, and then I simply have to do a for loop where I'm looping through these layers. And I hope that's it. I'm missing something in the syntax. No, batch first should be true because the first dimension that the transformer should encounter is the batch dimension. For dash in layers, what am I missing? In range of layers, but then still I'm missing a bracket, I think. Range typo. Okay. How about now? Why is this coming? I'm not understanding. Self dot transformer blocks equal to nn inside, but that I have here, right? Am I wrong? I think this should come afterwards. Yeah, obviously. Yes. Yeah, for sure. Yeah, I think now it's fine. So we have now transformer blocks where each of these transformer encoder layers, which will include attention head as well as multi-layer perceptron, repeated n number of times, where n is the number of layers. Okay, and now we need self layer normalization. So self dot layer norm equal to, do we have option to give hidden size of MLP? Yes. No, I think it's by default it's 4x, but I'm pretty sure it's that option exists for sure. Yes. Self dot layer norm equal to nn dot layer norm of dim embed underscore dim and self dot head underscore CLS. So now we are coming to the CLS tokens classification head, and we need one like this, self dot distill underscore CLS. So CLS, sorry, distill underscore head. So we have two classification heads, one for distillation token and one for CLS token. Now this will be the item number 0. This will be item number last. So nn dot linear of, and here we are going from embedding dimension to, what are we doing in the classification head? We go from embedding dimension to something. What is that something? Number of classes. Embedding dimension is maybe 32, 64, whatever. Classes is 10. So we go from that to classes. So classes we have to pass here equal to classes. And same thing applies for this. This is also the same. So these are all learnable parameters, by the way. Whenever we have nn dot sequential, nn dot linear, everything inside that is learnable. I think that is pretty much it. Layer norm. Yeah, sure. I think that's all. Now we just need to do the forward pass for every token. So define forward of self comma x. And then we say x, or first we need to extract the batch size, because this we had discussed in the last lecture. If we do not extract, if we keep using batch size as a variable, there might be some batches towards the end whose number of elements may not be 12. Maybe it has only 9 elements. Maybe it has only 7 elements. So the safest thing always to do is extract the number of items in your current batch by looking at the 0th dimension of your input variable. Then x equal to self dot batch underscore embed this one of x. So now you have patch embeddings. X is converted into patches. Then you define CLS token. So CLS equal to self dot CLS. But one thing you have to do here is CLS token. How many CLS tokens do you have? Here you have only one CLS token. but you have to expand it along your batch dimension. So say self.cls.expand, because you need one CLS token for every items in the batch. B comma -1 comma -1. You are only expanding along this dimension. Rest of the dimensions remain untouched. Second dimension is the number of batches. Third dimension is the embedding dimension. Now, distillation token dist equal to self dot distillation dot expand B comma -1 comma -1. Same thing. So class token and distillation token they have no difference. The only difference is where you are appending them. Class is appended, prepended. Distillation is appended at the end. Now we say torch.concatenate. So torch.cat. Here you are concatenating three things: CLS, comma, following CLS, what should you write? CLS, comma, something, X, comma, dist. Can you do something like this? Can you do dist, comma, X? Can you do this? You can do that also. I mean, I don't think there is anything conceptually preventing you from doing this. Only thing is you have to be careful about which context vector you are extracting at the end. In one case, you will extract 0th and n+1th context vector. In another case, you will extract 0th and first context vector. That's the only difference. But here, let's keep it as the original data efficient image transformer paper. So class, comma, CLS token, comma, X, comma, distillation token. So you are concatenating and comma 1, but this concatenation happens along the I would say first dimension, because 0 dimension is batch, first dimension are the tokens. But then to this you have to add a position embedding. So in the last lecture, if you remember, we had expanded the position embedding also, but it's not strictly necessary, because if you simply add this self.position, this will Python will automatically do something called broadcasting. So see the issue here. Position has not been expanded. So position is still, it is assuming that the batch size is 1, number of items are n+2, and last item is embedding dimension. But here CLS token is taking B. B is mostly 12. So here the dimensionality is 12, comma, n+2, comma, 32. But position embedding is 1, comma, what was the second one? n+2, comma, 32. So now you might wonder, how do you add two tensors where one tensor is of dimension, the first dimension was the B, batch size 12. Second dimension is number of tokens, which is n+2. Third dimension is embedding dimension, which is 32. How do you add that with position embedding, whose dimensionality is first item is only 1, second item is n+2, third item is 32. So Python automatically does something called broadcasting, where even if you have not expanded the self.position along the batch dimension, when you are adding, here that broadcasting will automatically take care of it. So you don't have to explicitly expand this along the batch dimension. Then X equal to, so this is where you now have all the tokens with position embedding. Now you pass it through your transformer. So now you say X equal to self.transformer blocks of X. And here actually you have to pass it, here you don't have to pass it 3 times, because you are not calling multi-head attention. If you were calling multi-head attention, you will do X, comma, X, comma, X, Y. 1 for creating query, 1 for creating key, 1 for value. But here, this is the whole transformer block itself. So you don't have to do it explicitly. So self.transformer blocks of X. Then you do layer normalization. So X equal to self.layer norm of X. Now you are ready. Now by this time, you will have both tokens ready to be extracted. So CLS underscore token equal to 0th item X of 0 for every batch. It's the 0th item. And similarly, distill token underscore token for every batch, it is the last item, which is -1. Very good. I'm glad you are paying attention. So now you have distill token. Now you have CLS. Now what you should construct? You can construct logits. So CLS underscore logits is this extracted CLS token now has to pass through this head self.head CLS of CLS token. And similarly, distill logits. So this is before the softmax. You're just taking the logits equal to self dot head distill dot head distill, and here you pass the distill token. So now you have the CLS logits and distill logits. I think that's all you need. You can now simply say return these two logits. Softmax you can calculate later. Return CLS logits and distill logits. So by this point, you will be ready to have the logits used for loss calculation. So loss we have not defined yet. The KL divergence loss we are yet to manually define. But before all of that, let's just run this to see if there are any syntax issues or not. I'm pretty sure something or the other might. Okay, luckily it has run. I don't think there are any issues. Now, one thing we should write is define student model. So student equal to, now what is the name of the class? VIT of dot to device. So just like how we pass teacher into CPU or GPU, same thing we do for students. And optimizing parameters are all the parameters in the student. So torch dot optim dot adamw student dot, so this is the same student I'm pasting here, basically dot parameters. So I'm optimizing these parameters. And how am I optimizing? I'm optimizing it at a certain learning rate. It was LR underscore learning rate underscore student, if I remember correctly. This was the variable that we used. Okay, so that is also done. Now we can perform the distillation, the KL divergence loss. So let's say define the loss function. So in the loss function, define, this is just a function. So KL divergence loss is, so here what are we passing? We have to pass some logits from the student. So let's say student logits. We have to pass some logits from teacher. So teacher will make some prediction. So teacher logits, and alpha or lambda for defining how much weightage we should give to both losses, loss due to difference between distill token and teacher, and loss due to difference between ground truth and CLS. So alpha equal to alpha. We had defined alpha as 0.5 earlier. Temperature also we need temperature equal to temperature. Then we need to define two losses, KL divergence loss and second one. So this equal to something, KD equal to something. Second was cross entropy, CE, cross entropy loss. And when we finally return, we will return something like alpha multiplied by, so it was alpha multiplied by KD and 1 minus alpha multiplied by cross entropy. So plus 1 minus alpha multiplied by cross entropy. So this is the final combined loss. So now we have to calculate individual loss. Out of this, cross entropy is the easiest. So that is F dot cross underscore entropy. And what should I pass here into cross entropy? What are the two things that I'm passing? Oh, one thing I forgot here is Y. Y is the actual ground truth. We are passing CLS, the logits from the S from the student, and the actual Y, which is the ground truth, right? So S logits, comma, Y. Y is the ground truth. We are yet to define the ground truth Y because we have not extracted it yet, but that we will come to in a bit. So in the S logits, we will selectively pass one of them depending on, S logits dot, yes. It should be should I pass each of them separately? Maybe. No, I think this is fine because see, in student logics, depending on what I'm passing, I can simply pass the logics corresponding to CLS token here while calling the function. So this is fine. Writing like this is okay. Okay, now KD is f dot, there is a function called KL underscore div, KL divergence. And here we have to use softmax because so far we have not touched softmax. In cross entropy, softmax is inherently coming. So we can pass the logic directly. But here we have to do softmax. So softmax of S underscore logics divided by T dot dim equal to comma dim equal to -1. Now is T defined? No, it's only temperature. And so this is the softmax for student and comma. So KL divergence is calculated between students, this and teacher. So teachers is F dot softmax, teacher logics, temperature is temperature, dimension -1. So here, when I say student, it can be CLS or it can be distill. It can be either. Maybe one way to remove your confusion is, let's say, I call it this as CLS logics and I pass distill underscore logics. And then CLS logics I use here. Distill logics I use here. I think now it's cleaner. Am I missing anything? I think that's mostly it. Let's run. Okay. Now we can run the epochs. So at hash title epochs, and running epochs is independent of code. So I can directly take my epoch code from the what I have already written. Okay, so for E in epochs underscore, I'm not sure if epochs underscore student is the variable. Okay, it is. So for E in range of epochs underscore student, student dot train. Student we have defined over here. So student dot train means our vision transformer will be trained. For X comma Y in train underscore data loader, for X comma Y equal to X dot to device, Y dot to device. So images and corresponding labels. And with torch no grad means you are purging the existing gradients instead of letting it accumulate. This is something that standard you do if you are running on small data sets. T underscore logics is teacher of X. So teacher we had defined up here and we had passed teacher to device right above this block. So teacher equal teacher dot to device. So we are passing into that our input X. And then CLS underscore logics and distillation logics are output from the student. So why am I writing this comma this? Because in the return, if you remember, we are returning CLS logics and distill logics from the vision VIT class. And then my loss is KD loss, but here I'll make some change. Here, instead of distill logics, I will pass CLS logics, distill logics, teacher logics, and Y. So CLS logics, dist logics, teacher logics is T logics, and Y. So this is the CLS token logics. There's a distillation token logics. This is the teacher's logics, and this is the ground truth. 4 things. And if you remember from our diagram, we had mentioned that you need 4 things for calculating the loss. From distill, from CLS, from ground truth, and from the prediction of the CNN, which is the teacher. So now we have all the 4 items. And I think we are ready to just run this. Let's see. I hope. Okay, some issues there. Name student is not defined. Maybe because I have not run that block. So I'm just running the whole thing once. Got an unexpected argument dim. Somewhere I'm using dim instead of embed dim. Okay, dim equal to -1. Not -1, this should be 1. Because for each batches, we are calculating this for that particular token, that particular context vector token. Maybe that is the issue. Got an unexpected self.transformer blocks equal to, okay, its issue is there in this line, I think. Maybe I just need to pass like this. Yeah, I think now it's working. So the issue was here I was passing it as dim equal to query key value space dimensionality. You just need to pass the query key value dimensionality. You don't have to say dim equal to that. So this one line was the issue. I think it is running. Let's see. Yeah, I think it's running. This warning, I know what fixes this warning. There is some extra parameter that we need to add here, something like reduction equal to batch mean. Although I don't know what exactly it does. I know that it can get rid of the warning, but let's run it without that anyway. So this is just the training epoch, and then after this we can run validation. So let's paste that so that once this is finished. So test DL. I don't think test DL is defined. I think this is validation data loader, val DL. I think rest of the things are fine. And once validation is done, we can display some sample image from our predictions. So this is again not anything specific to data efficient image transformer or vision transformer. It's like for any deep learning. So I don't want to write this code and spend time here. Let me try stopping and asking Gemini to explain this. Or let me just try adding that extra parameter here. Reduction equal to batch mean. Oh yeah, I had forgotten this temperature raised to 2. Yes, this was missing. I think Gemini gave me the suggestion. This was completely missing. As we discussed, if we take the softmax derivative, 1 by square of temperature term will come. So to nullify that, you should have a temperature square term. So I hope this may fix the issue, the warning, but let's see. Yeah. We can ask actually GPT, what is this batch mean thing actually doing? And meanwhile, my code is running. Let me know if you guys are also able to run the code on your end. I am running this on, I'm not sure if this is GPU or something. I think this is just CPU. Maybe I'll change the runtime. I'll use this TPU. But this code was small enough. I had one extra line here just to try with a smaller data set. So I think this original MNIST data set had 60,000 images or something. So I just wanted to try with 6,000 images. So I had written one extra block of code for splitting my data set into just 60,000. Then this training will be faster. But anyways, this is not too bad. But let's bring the splitting part of the code. So this was a splitting part. If I say n equal to 0.1 times len of the training data, then I'll only pick 10% of the data for training and validation, just the total 10% from my data set. Actually, let's try that. Actually, this is a bit slow. I don't like it. So train, okay, n equal to int of train ds. Then subset is that of this, and we have to import subset. And train ds equal to this. And this is train underscore full maybe. And validation, yeah, validation can remain as such. I think most of the things are fixed now. And n equal to 0.1 times. So only 10% of the data is used for training. Let's see whether this works. Okay, this is faster. Has anyone managed to run, guys? Is the code working for any of you? I'm pretty sure you can see the latest version of the code with you. Okay. We can do some interesting things. So here, the loss, or rather in prediction, let's see what kind of token are we using. So just look at the prediction. So prediction is, actually, let me comment this out and let me only use distillation token. So right now, if you look at what we are using for prediction, I'm just using the argmax of the distillation token. So in the paper, they had tried distillation token separately for prediction. They had tried class CLS token separately for prediction, and they had tried combined. So combined is simply I can just add CLS logits, distillation token logits, and divide by 2. Okay, test accuracy 3.3%. Let's see what's going on. First, let me do one thing. I will uncomment this, and then I will use CLS and distillation. That's the first thing I want to do. Second thing is I just want to make sure that in my validation batch size is not too big. So I'd be much safer to directly use this block of code. So train DL, data loader, and now I just need to use test DL and train DL and wherever I'm calling my model. So this should be test DL. Yeah, I think that's all. Just let me know the accuracy you guys are getting. Earlier I was getting 95%, 88%, something like that. But let's see. Has anyone managed to obtain pretty good accuracy, like 80% or above yet? Okay, okay. So right now, maybe I can just reduce the whole architecture size a little bit. I just want some results to be initially seen, and then we can see. Epochs is 5 only, and this is a reasonably small architecture, so I don't think running should take so much time. I don't know why is it a bit slow right now. Earlier when I was trying to run, it was definitely much faster. I may have the residual output from it's not there. If any of you have Collab Pro, I also loss need not be log softmax. Log softmax is just used for preventing the things from blowing up, the softmax exponents from blowing up. But here, I don't think you are talking about here, right? This should be log softmax, and this should be. I don't think it's needed because the actual formula is softmax. It's not log softmax. And KL divergence will automatically take care of the rest of the things. But the arguments that you are passing into the function is the softmax of the logits, right? Logarithm is taken within the KL divergence formula. So to my understanding, we don't need this. We don't need to use log underscore softmax here. For anyone, is it taking this much time? I was trying this, but it was much faster for me earlier. For some reason, right now it's very slow. Okay. Let me actually pause this and maybe I can try over here. Okay, one difference is here embedding dimension is much smaller. So of course that will make things a bit faster. And let me keep just one epoch. How about that? Yeah, it's already one. So at least we can see the last result, how it looks. Test accuracy 10%. Wow. Yeah. Here we took one out of 10. Yes, yes. We split the data set by saying n equal to 0.1. So test accuracy 10% is completely, it's the worst possible model. But let's see. I was able to get 95%. I just don't remember what hyperparameters I used, but I'm pretty sure we can get there. Here I'm not sure if I think you were mentioning whether this n is, yeah, this should be 0.1, then it will be a bit faster. Okay, so now we are using only 10% of the data only for one epoch. Hopefully this should get executed in a reasonable amount of time. Okay, it is done. Test accuracy 43%, not bad for one epoch. And these are my predictions. So since only 40% is correct in test here, 7 is correct. 7, this is wrong, this is wrong, this is wrong. Most, only 1 out of 5 are correct. But now let's increase the number of epochs. Oh, 1 is too less. At least 2 or 3 we can keep. Let's keep it 3. And let's see if this runs faster. I'll actually share this code link. I don't think anything is in principle different between this, my previous code and current code. It's just that hyperparameters, maybe I have messed up something. I just cannot figure out what. But just try this code. I have just pasted the link. Okay, slightly improved, 56%. And one thing I can do is, instead of using distillation token alone, maybe I can use both CLS token and distillation token for predicting the testing. 45%. Okay. So clearly I need more epochs. So let's keep it 10. And the rest of the things can stay as such. And let's run. Yeah, I think in one of the lectures or maybe on Discord we can discuss about important sampling. I'm not planning it as part of a lecture, but probably we should discuss about it at some point. Yes. But try this code with 10 epochs. I hope you will reach close to, I don't know why am I not getting, what did I do different to not get a good classification accuracy yet? I'm doing everything correct. So the loss is taking into consideration both while making the prediction. So CLS underscore distillation. So both are being considered. So I'm taking average of the logits from CLS and distillation and then taking argmax of that. And that is what I'm denoting as the prediction. I know one conceptual thing that we should do better, which is we should do fine tuning of the last layer of CNN. Okay, now test accuracy is much better, 83.24. Now let's see what would be the test accuracy if I use only CLS logits instead of CLS and distillation. What do you predict? If I just use CLS logits, will it be worse or will it be better if I run the code? The test accuracy, will it become better if I use only CLS logits instead of CLS plus distillation? Better or worse, in your opinion? Should be probably worse, right? Because, yeah, ideally the same, of course. But I think it will be worse because, no, I don't know why I think it will be worse. Maybe let me run and figure out. 7. Oh my God, there is something definitely wrong. If it is 7%, it's the CLS logits is not doing anything. What about distillation logits? The distillation logit is 85.85%. Okay, so clearly distillation is doing most of the things. Although my CNN is not very, last layer I have not trained at all. So this last 10 node classifier is like a really bad layer. Actually, I should do a little bit of fine tuning by freezing every single layer to make sure that this last 10 nodes are also not random. So even without doing that, right now teacher is doing most of the work. Ground truth is not helping me with the class token. But here are my predictions, display predictions. All of these are now, except I guess this one, all of them, other rest of the ones are correct. So clearly the code is working. It's just that we have to figure out why CLS token, if I just use CLS token, why the testing accuracy is so low. Maybe uh, let me test on more number of samples, I guess. Len of samples. I guess that's not changing anything. So what we are observing is distillation token is performing the best. CLS plus distillation token is performing somewhere in between, and CLS token alone is performing the worst. That's what we are seeing here right now. But this is extremely surprising to me because when we implemented Vision Transformer, we were getting very, very good results. How will you freeze other layers? Oh, that part is actually very easy. The code is actually very easy. I don't even have to write from scratch. I can just ask Gemini. Here, freeze all the layers and train just the last classification layer. So it's only like 3 lines of code or something. Yeah, CLS logics are actually trained with ground truth. So it doesn't make sense to me why the accuracy for CLS token is very bad. I have to check a little bit in depth why this is happening. Yeah, I think that's it. So for param in teacher.params, params.require grad is false. So every layer except the last fully connected layer, you are not passing the gradients through that at all. So now, okay, let's try this. Let me train the teacher. This code is already shared with you, but let's see what happens if teacher is slightly better. I don't think it should make any difference, but maybe it does because teacher not just influence distill token, right? Teacher, the loss that is present, the global loss is influenced by teacher as well as ground truth. Global loss influences the all the weights, and if all the weights are changed, basically both CLS token as well as distill token, both of them changes. Not necessarily, right? So if we change the teacher model is influencing the final loss, and it doesn't matter where the loss is coming from, whether it's coming from distill or CLS. Finally, it's influencing the weights. So learning rate is 3 times 10 to the power of -4 in this case. Yeah, that's true. Learning rate could be it could be higher. I should probably do a grid search of different learning rates. I'm happy with 85%, but I'd be happier if we got something similar to Vision Transformer. In Vision Transformer, we got 90, 96, 98%, if I'm not wrong. But here, let's see with a teacher whose last layer is also trained. Let's see what's the output looking like. Okay, definitely something is wrong here. It can't be 4%, whatever it is. So, but if I use CLS and or if I use only distillation token, 81, somehow a better studied teacher is performing worse. Let me do one thing. Let me play with alpha a little bit. If I keep alpha as 0.1, so what does that mean? It means 0.1 means scale divergence is only 0.1. Ground truth, I am paying 90% of the attention. Not attention, I mean weightage. So let's see now what happens if I run. So now it should be more like a normal Vision Transformer, because in my loss, 90% of the loss is due to cross entropy loss between CLS token and the ground truth. 10% is the loss scale divergence loss between distill token and the teacher's prediction. If this experiment is not giving us better result, we'll stop at this point. Anyway, I highly recommend you guys to play with the hyperparameters like learning rate, play a little bit with maybe the number of attention heads, embedding dimension. I'm using 16. Maybe do we need 64? Just try that. Just play with a little bit of hyperparameters in this, like an ablation study, and just come up with what works best for this particular data set. For whatever reason, I am not able to replicate the like 95% results, which I got for the same code for a different set of parameters earlier. but now we are able to get only till 85%. One thing that is missing is we haven't written the training loop for teacher. So how come teacher will learn right now? We have just mentioned the condition. I forgot to write the training loop for the teacher. So that is missing. So maybe my thinking is maybe the teacher is not at all giving good predictions right now because the last layer is not trained. And because of that, the model is really bad. Okay, so now test accuracy is 85 with distillation. With CLS, it's again very bad. And CLS dist 80. Okay. All right. Anyways, that is all right. These are some of the tests. In these tests, most of them seem to be correct, except this one. Prediction is 4, ground truth is 1. These are actually simple images to make prediction on. I don't know why 1 is getting predicted as 4. So it clearly shows that the model is not very good. Because if the model was good, it would get confused on, okay, you got CLS. Oh, really? CLS logic 95%. I'll be very glad to see your hyperparameters, what changes. I have never managed to get CLS logic. I mean, I have not spent too much time on this, but whatever time I spent, my CLS logic was always performing the worst. Himanshu, you can feel free to share your code on Discord. We'll take a look at it. But I hope, guys, you understand the basic idea. The whole point is you can use a teacher that is well trained on your data set, and I mean on a global data set, and then you can fine tune it if needed on your data set. If your data set and the public data set on which the big teacher model was trained on are completely different, and then use the teacher model to guide a distillation token's loss, and thereby the weights and bias parameters in your model, right? And that way you can get the student to mimic that of a teacher. So here it's sort of like compressing the teacher's abilities. You are compressing it into a smaller model, sort of. So, and this idea is not introduced by data efficient image transformer for the first time. There are other papers that explore this idea so much, but this DEIT paper came out at the right point in time, because vision transformer showed that it can achieve state of the art, but people did not like it too much, mainly because firstly, the data set, the JFT data set was not publicly available. So replicating exact results was not possible. Secondly, to run it itself, an individual cannot run. Like you and I cannot probably run train a vision transformer completely from scratch, just like how Google did it. So that was another thing. But this data efficient image transformer, this is something we can replicate from this paper. Whatever results they have, we can definitely replicate it ourselves, because it's reasonably small. You don't need insane computational resources. Dataset is also publicly available, and still you are able to get something close to state of the art. So that was the significance of this paper. I really encourage you to okay, learning rate is smaller, so I am using a higher learning rate, I guess, right? 3e minus 4. Instead of that, maybe 10, just 10 to the power of minus 5, or 1e minus 4 or something like that. If I use, perhaps it'll be better. So this I should change. Okay, while I wind up, I'll just run it in the background and let's see. So please have a look at this paper. I'm sure you are going to have a relatively easy time understanding this paper if you have understood how vision transformer work and how the architecture of data efficient transformer is. It looks like long paper because it's 22 pages, but in fact it's short, because look at, it's just one column. The margins are so huge. Some pages are just tables, like one of this page, or not this, where is that? This one of this page is just a huge table. Yeah, this one. So, and last few pages are anyway references. So this paper was, I had a relatively easy time reading this paper. Usually papers drain a lot of energy from you. You need multiple hours to sit, but I have maybe read this 3 times at this point, the paper. First time it took me maybe 3.5 hours. Last time I read, maybe I could finish it in 1.5 hours or something. So I know that as a scientist, we should not think about length and all those things of the papers. But as a human, of course, when you see a giant paper, you always get intimidated and you probably have less motivation to read it. But this paper, from that point of view, this paper is easy. So please have a look at this. Please try to replicate the code, try to achieve a better accuracy than what I have showed you, because clearly you can play with the rest of the numbers to get good accuracy. It's just that I haven't played with it. You guys can play with it on your own time. I hope you enjoyed today's lecture. In next lecture, most likely we'll be learn about shifted window transformer. It's another approach where people try to bring the idea of CNN convolution into vision transformer. So it was a beautiful paper, very high number of citations. We will hopefully build that also from scratch. One thing I want to address is these lectures, of course, are going longer simply because I have decided to add coding from scratch as much as possible. So I know that it's not ideal for many of you. Maybe you want to leave earlier, but I think you will have the best learning experience through deep work and long thoughts, right? So you have to sit down and code. So I could do this lecture with just the theory and very little coding from scratch. I could just run the code myself, and I could stop the lecture at 12 p.m. But if I do that, I don't think it'll be fun for any of us. So thank you so much. We will meet again next Saturday. Take care until then. I will try to post 3 assignments this week for all the guys in Pro. One for Vision Transformer, one for Nano VLM, and one for DeiT. But I will not impose like a 1 week deadline, because that way, you guys can take your own time to wrap up the assignment. So just have a good time coding these models from scratch. We will move on to detection transformer after this. So far, we have not discussed about object detection or segmentation using transformers. We have only discussed about classification, but detection, as you know, is the, I would say, classification is the gold standard, but detection is, of course, more difficult and more useful task. So we will come to that. And Pro is not different. These are all part of the Pro, but Pro folks have access to my files, handwritten notes, etc. But anyways, see you next weekend. Take care until then. Try your homework, and let's meet in by next Saturday.